I want to start off this video by traveling back in time, about 400 years and some change. Let's say it's the year 1595, and Galileo is experimenting and working, and he is utilizing Euclidean math to make calculations. And what he figures out through his calculations and utilizing geometry, this geometry that has been passed along for like 2,000 years at this point, is that the math doesn't add up according to the way that people think it should, right? And according what he does is he makes calculations of the distance between the Earth and the Sun, and then he finds out that essentially by utilizing these mathematical calculations that it's mathematically impossible for the Earth to be the center of the universe, right? That is just with everything that is known about geometry and assuming that the geometry is correct and everything like that, and that 2,000 years of this geometry at this point is correct, that he's on to something. And then so that's where Galileo essentially, like, that's how it all happens, right? Is he just is doing math, figures out it doesn't check out, and then people they criticize him because it's 2,000-year-old math, right? And then it's like, well, math has been around for 2,000 years, and this is the way that it was. And then what makes you say these things and come out? And then he's, well, there's deviations in the math, and then even some scholars at the time, like those big, huge astronomers, they disagree with Galileo, right? Because they side with tradition and the 2,000 years. And then this argument of kind of these variables that can be thrown out. So you can see it's kind of a pattern that exists throughout physics as a whole. It's starting with Galileo itself, like the foundation of modern physics, and we can see the tracing before that it's just human when you have kind of like an equation or this will solve 99% of things, and then we just have to throw out this 1% variable sometimes. And if we just ignore that 1% variable sometimes, then everything checks out. Then the human tendency is to just utilize that 99% problem until you run into the 1% problem, right? Like it's just a conservation of energy. I think everything comes back to physics, right? It's normal conservation of energy says, why not just use that 99% equation as long as it works until it doesn't work? And then, or until someone finally proves the better equation, right? Like here is the definitive mathematical equation that the Earth is not the center of the universe. And then so fast forwarding to the present, why does it matter now today, right? And then so now today, we have this 1% problem again when it comes to physics. And then with this 1% problem, we're running into it more and more. I see it like I keep track of everything that goes on with like the Hubble telescope and the James Webb telescope, everything like that, and you can see that there's more and more anomalies that come up, right? And then I classify these anomalies into three categories: dark energy, dark matter, and Hawking radiation. And Hawking radiation tying specifically to black holes. And then so these three areas and what come out of these three areas are kind of our 1% of understanding right now with regards towards the universe. So our current universal understanding is that the universe is Euclidean in nature, right? Euclidean in shape, going back to the same math that Galileo utilized and that was prevalent for 2,000 years before Galileo. It's still prevalent now, 400 years and change later. Right? So it's still the same math, this Euclidean math, the same one guy. and so within this, we base a lot of assumptions off of this one mathematical concept. And this one mathematical concept is that the universe is a flat concept, a flat, ever expanding flat space that is infinite on both sides, right? No start, no end, and it's like a flat line. And that's how a lot of people are taught. That's how the universe is. That's the shape of the universe. It's just like kind of like this, somehow this flat line, and it's with no start and no end, which is the definition of Euclidean space. Right? And then so And it makes sense that people don't question that for a long time. But so around this same period of Galileo, you have another figure that comes out as well, Sir Isaac Newton. And then you have kind of Riemannian geometry, and then some shifts of geometry. It's like, so this is the birth of modern physics in this era, right? And then one of the very first things right after this that they hit on is that there's challenges with the understanding of geometry in this era, right? And then so Riemannian geometry gets invented in the same era for this same reason. And Riemannian geometry is important because that's the kind of the basis for hyperbolic spaces and hyperbolic geometry as we know it now, right? It wouldn't exist without that invention. And so hyperbolic space, if you're not aware, it's just very simplistic in that there's a curvature in space itself, like a bend in space itself, very simplistically, right? And then so that curvature makes space, we'll call it round. And then so what would be, I'll start with, before we dive into experimentations within this, I normally I don't like to utilize ChatGPT and like in these types of instances, but like I figured the response is so good in this instance that I want to utilize it very specifically to highlight this. And then so I just ask it a very innocuous prompt, right? And I want to show the prompt first, which is, can you provide a list of all of the updates to current physics knowledge that would be made if it's proven that the universe is hyperbolic and not Euclidean? And then its very upfront statement is, if it were definitively proven that the universe is hyperbolic, negatively curved, rather than Euclidean, flat, it would fundamentally alter our understanding of physics, cosmology, and the nature of space-time. Essentially, we would have to update space-time geometry, cosmology, quantum physics, particle physics, gravitation, thermodynamics and entropy, the way that black holes work, astrophysics, high-energy physics, mathematical physics, observational cosmology, philosophical and theoretical implications are 11. So we would have to update essentially 11 parts of physics just off of this one observation, right? If this one observation were proven true. And then it lays out the overall impact here. So summarization, right? Proving the universe is hyperbolic would revolutionize physics, from the most fundamental laws to practical astrophysics and cosmology. It would also provide a natural explanation for many unsolved mysteries, such as the cosmic microwave background's hot-cold spots, which we'll get into, the origin and nature of dark energy and dark matter, which we'll get into, and the Big Bang's initial conditions and the large-scale structure of the universe, which we'll definitely get into. And then so, within this overall impact, this at the top I mentioned kind of three things, right? Dark energy, dark matter, and Hawking radiation. And then so why those are important within this is that, so within our current Euclidean understanding of the universe, we have these three concepts that emerge because they emerge that 1% rule, right? That 1%, we need to throw stuff out. Our equation only works 99% of the time. So we've invented dark energy, dark matter, and Hawking radiation to explain that 1%. But none of them and all of them in conjunction don't fully explain the 1% still. But they're what have been invented to fill this gap, right? Because we know that, like, for example, mathematically, there is more matter and energy in the universe than the Einstein equation states that there should be. So how do we account for that? We create dark matter and dark energy. But if the universe were hyperbolic in nature, meaning that there was a slight curve to the universe as opposed to it being completely flat, that mathematical discrepancy wouldn't occur in the first place. It would be explained by that small curvature. And then so, like, what we call dark energy would be in existence in that small little curvature line, like that extra little matter and energy that exists in the universe would be perfectly explained because that extra little matter and energy would exist in the universe. It would exist in the curvature itself. The fact that the universe is expanding in a lumpy matter as opposed to a straightforward matter would also be explained by this. And so essentially my upfront proposal is that everything that is mathematically related to this 1% problem within physics is magically solved if we just re-envision the universe as a hyperbolic universe as opposed to a Euclidean universe. And then so let's dive into some experimentation as to what this would actually look like, right? And then so this is what gets me started first of all on this track. And then so I'm experimenting in this first experiment with hyperbolic distances and understanding clustering within hyperbolic spaces. And then so I just run a bunch of experiments where I just have clustering, like I want to see clustering happen, right? So like this is kind of like a bomb going off in the space, right? And so it's what you see. I want to see what happens, like how does it disperse? And then what you're noticing, to me, if you're not paying attention or don't know what to look for, is that this isn't 100% even dispersion, right? It's not uniform. It's not a cool pattern. If I dropped this same experiment into Euclidean space, this contraction and coming back together, it would always be uniform. It wouldn't be as randomized as this is. And then so this clustering effect, the fact that they always want to cluster, but then the fact that when they spread out, it's not uniform expansion, is you only get this in hyperbolic space. You don't get this in Euclidean space. And then so my first observation is that this more accurately represents what I know about clustering dynamics and clustering behavior within real world settings, as opposed to Euclidean space. So when we go back and we like those outliers, those 1% outliers, clustering dynamics within Euclidean space as a part of that. Here's an experiment here that you can run yourself, very straightforward. And what we can see is that if we just look at clustering dynamics in hyperbolic space and we run simple experimentation here in hyperbolic space as opposed to Euclidean space, that it rectifies itself. The problem goes away, right? And then so second problem is that all of our observations and all of our recent observations have shown two things. One is that there's a quote-unquote lumpy expansion of the universe, meaning that the universe is expanding infinitely, but it's not expanding infinitely in all areas at the same time. Like kind of weird, right? It's lumpy. And then the second thing and second observation within that is that matter it's not a uniform dispersal of matter throughout the universe, and especially within the early universe. This comes into like models of the Big Bang. And then so when you model like the Big Bang under and in Euclidean space, what you would expect is a uniform dispersion of matter, energy, etc. in that space. And the reason why scientists keep coming back to this and why we keep talking about it and why everybody keeps talking about it is because that's not what happens, right? And when you recreate the simulation, it's not a uniform dispersion of matter that occurred within the early universe. The simulation doesn't match. So what happened there? What's the difference? If you look, so this is the density and variance of hyperbolic space. And then so this is what a universe would look like if a universe were hyperbolic and then were projected into 2D space. So this is like a 3D like circle type of object, but it's flattened into 2D, right? So that's kind of what we're looking at here. And then, so first thing that you notice is that there is a big hole in the center of this universe, right? And that would be common. And so what would fill the big hole in the center of this hypothetical universe would be black hole or black holes, flat out. And then you would have lumpy expansion of this universe. So this universe would be infinitely expanding. And then so around the theoretical, the barriers and the outer layers of this would be theoretical, right? But around those areas, if you were to measure in those areas, you would have lumpy expansion. And then also just noting within this, the reason why it's all this different colors and all these different rainbow colors is that's different temperatures and different energy levels within the spread out, not uniformly, more along a chaos theory and following the dynamics of chaos theory as opposed to like a uniform linear approach within the energy dynamics within this type of space. And then so just very coincidentally, everything that I just outlined there are very coincidentally it lines up observationally with the universe, right? But so according to the current universe, the universe is like this. It's a flat line somehow that is just, it's a flat line as opposed to a structure like this. And then in the center of this flat line, we know that there's black holes in the center of there. I don't know. I'm just so let's go on to the next experiment here within that, and then so the next experiment that I want to do. So going back to this black hole or Big Bang theory, right? So we have again, if we simulate the Big Bang and kind of that initial conditions, and we look at it in hyperbolic space versus Euclidean space, we're going to get two different answers and two different outcomes to the same experiment. So if we do kind of a Big Bang in hyperbolic space, I want you to notice and pay attention to the outliers more than anything else. So look at the very top here, like at the very top of this where you see, and you'll notice that there's more. That very top there is hotter than it should be. And if you look at this and you look at small areas, you'll notice that there's some areas within this and within this dispersion that are hotter than they should be, and some areas that are colder than they should be. And it's very minute, but they're there with regards towards this dispersion, right? And then we model this over time, and it's that same thing. As it disperses out at a relatively even dispersion pattern, but there is there's unexpected patterns within this pattern, right? Unexpected hot spots and cold spots that appear, and you can just point them out and look at, like, this area is hotter than it should be here. This area is hotter than definitely hotter than it should be right here, right? Here, and etc. Right? And then so just pointing those out. This area is significantly colder than it should be, and then so just highlighting that, and that this continues out throughout this expansion, right? And then so this is wave simulation within hyperbolic space. And then so what's this same thing look like within Euclidean space then, as kind of the control? Exactly as you would expect in your imagination, right? And then so remember, this is a 3D space flattened and projected onto 2D space. So like this is like where it's the hottest here is kind of like the center of the explosion, right? And then so it's going to expand from the center of the explosion. And that's exactly what happens, right? It starts getting hotter and hotter away, and that heat dissipates in an even, uniform, very uniform pattern away from the explosion, right? And then essentially like the whole universe gets hot in an even expanding way, as people would expect it to operate within Euclidean space and within early Big Bang theory. But this is not what the simulations point to. The simulations point to this, right? So just highlighting that. And then so last thing, we'll just overlay these on top of each other, right? So then just the kind of the last proof. So our wave stimulation in Euclidean space, we essentially, like, again, we drop like a big energy bomb in the Euclidean space, and then we get even dispersion of energy, right? Even dispersion of the hot regions and the cold regions. We see here the regions that are the furthest away from the explosion area are the coldest, as expected, and then it goes in a pattern, right? And it's kind of directed in like an arrow, kind of as to the heat pattern. You can see that, and it's very clear how exactly that heat dissipation is going to operate within Euclidean space, as opposed to hyperbolic space, where we're looking at here, right? Where again you have anomalies within the heat dispersion, where you have hot spaces that shouldn't be there, cold spaces that shouldn't be there, and it's because you have clustering dynamics. The reason is again, you see the shape of this blast is totally different as well, right? And then so within Euclidean space, you get a blast that's very, like, it's just spread out. There's nothing within space itself to stop the spread of, or shape the spread of the blast. Whereas if a blast occurs within hyperbolic space, it's more circular like this. And then because the space itself exists to as a pushback on the blast radius itself, right? That's what occurs within that. And then so that and also enables your clustering effects within that. And then the clustering effects are what then enables and what accounts for these kind of hot cold effects and these hot cold regions within hyperbolic space, right? And so I'll leave it here and with that, right? And then like the big thing to conclude with that is, okay, so even if you don't want to take the leap forward that the universe is hyperbolic shaped as opposed to Euclidean shaped, within this, what you can take away is that there's differences within hyperbolic space and the physics of hyperbolic space and how it operates compared to how we think it should, right? And then so within that, I deal with that a lot. I talk to PhDs on a daily basis, specifically like around this, right? And oftentimes it's it's the same thing. Like they'll throw out variables like it's this just operates and it's just a function of the space that we don't understand yet. And to me that doesn't exist. Like it's a function of the space that operates off of physics, off of a pure physics. And if you understand and you just overlay the physics, then that's it, right? Like if there's an anomaly within the equation, then there's something that needs to be adjusted within our current understanding. And then once you do that, it fixes the problem, and you don't have to go through giant leaps like dark energy, dark matter, and how Hawking radiation works. If you just make one simple change to the equation, all of that falls off and it all makes sense. And if you like this type of content, please like and subscribe. Thank you very much.